Okay, guys, here's the second video in the series. All right, so now we're going to talk about aluminum. Okay, I'm going to just make it here so it's a little bit easier. Al. Okay, and this is element number 13. Okay, so just like the last video, we're going to go through the electrical configuration and we're going to go through the whole process. All right, let me change my pen here to red. Okay, so just like before, we're going to do the electrical configuration. We're going to go through this a little bit faster since we should already know how to do configuration, right? So to get to aluminum is this guy right here. Okay, so we already know it's going to be in the third energy level. So it's going to be a 1s, 2 steps, 2s1, 2s2, 2p6, 3s1, 3s2, and then in the 3p, we take 1 step. So that's here. Okay, so this is the electron configuration for aluminum. Now, if I wanted to write this shorthand, right, it would just be 1s2, 2s2, 2p6, 3s2, 3p1, right? Now, remember, you can replace all of this, right, 2p6, you can replace all of that with neon, and then just write the configuration of the row that you're in. And these are all the same thing, okay? These are all the same thing. Okay, so we have the configuration done for aluminum. I want you to take a look at the orbital here, and I want you to start thinking about the question of how many more electrons you would need to completely fill up this orbital. In this case, we're still missing 4 electrons. So you would need 4 more. And this is going to be important in just a minute. 4 more electrons needed. Okay, so let's take a look at the ionization energy for aluminum. Okay, we know that aluminum, this is period 1, this is period 2, and period 3 is here. So aluminum is the 4th element, or the 3rd actually, in the 4th period, right? So it's sodium, magnesium, aluminum. So it's going to be this guy right here. In the 3rd period, it's going to be this guy right here. All right. So right off the bat, what do we see about the ionization energy of aluminum? Well, ionization energy, I'm going to abbreviate that as IE, right? Ionization energy is very low, very low. So if it's very low, is it fighting to keep electrons or is it trying to let go, right? So is it trying to keep or let go of electrons? Right? And that's the question you have to ask yourself, right? Is if the ionization energy is really low, right? And you still need 4 more electrons, okay? What is aluminum going to do? So let's take a look. Let's take a look, right? So I'm gonna do my Bohr model of aluminum. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And in the valence shell, we have 1, 2, 3, right? So if I was to do aluminum as a Lewis model, right? As a Lewis dot model, it would have 3 electrons in the valence shell, right? And let's take a look here. Let's do one more. Okay, so here's the part that I was trying to get at, right? Looking at the ionization energy, looking at the electron configuration, okay? Aluminum has a couple of options, okay? Option number 1, aluminum goes out and finds 1, 2, 3, 4, 5 more electrons, right? 5 more electrons. Did I say 4 up here? I did say 4, huh? Nope, it's 5. I apologize. Okay. Aluminum goes out and finds 5 more electrons, okay, and tries to get to 8 to fill up the empty shell, the half empty shell, right? or it takes these electrons and it gives them away, right? So it has the option to drop electrons. Pick up electrons or drop electrons. Now, looking at this, right, in terms of energy, is it going to be easier to go out and dig up 5 electrons somewhere, right? Remember, it's going to be 5. Or is it going to be easier just to get the 3 electrons that it has and drop them off to stay with a full shell here, right? That's what we got to figure out. So based on the ionization energy, which is really, really low, aluminum isn't really fighting to keep its electrons, right? It's just like, take them. So based on the ionization energy and the configuration, meaning that it's going to have to work way too much to pick up those electrons, it's going to go with the route of dropping electrons, right? It's going to drop them. It's just easier. So aluminum is in a position where it has, let me see here. Okay, get my pen here. Aluminum, right, has 13 protons, all right, and it has 13 electrons. So in its natural state, aluminum carries with it no charge. It is neutral. But we just said that it's going to drop off electrons, right? It's going to drop off electrons. So if I'm sitting at 13 electrons, and I get rid of these 3 electrons, 1, 2, 3, minus 3 electrons, I'm going to end up with 10 electrons, right? I'm going to end up with 10 electrons. So aluminum now finds itself in a position where it still has 13 protons. It still has 13 protons because you're not changing the identity of the element. But now, instead of having 13 electrons, it only has 10 electrons. It only has 10. So because it only has 10 electrons, it means it has 3 more protons than electrons, which means it's going to carry a net positive 3 charge. Therefore, making aluminum now a 3+ ion. And because the ion is now positive, we call this a cation, a positive ion. Okay? The process of aluminum ionizing to drop those 3 electrons, we call that oxidation. Oxidation. So the oxidation is the process of dropping electrons to gain / form a positive ion. And this is the notation for a positive ion. Okay? So this is oxidation. We just learned about why something would either oxidize or reduce, right, in the last video. In this case, depending on the number of electrons and the configuration and the ionization energy, we determined that would be more energetically stable for aluminum to oxidize 3 electrons and form a positive 3 cation. Okay? All right, guys. So that's it for this one. Thank you, guys.